You have to turn off that phone. Do I get to start? Sure. Well, we're very pleased today to have one of our own, Abanov from the Department of Physics and Astronomy and from the Simon Center, talk to us about on a Hamiltonian description of a fluid with Hall viscosity. And I hope he's going to explain Hall viscosity.
Hello, does it work? Yeah. Okay, it's my pleasure to be here and explain what I was doing recently, and thank you very much for giving me this opportunity. So the talk will be on the possibility to describe fractional Hall effect fluid in hydrodynamic language. And I hope that I did not oversimplify, but I will do a very elementary presentation, assuming that nobody knows anything except maybe for the word Hamiltonian in the title. And I'll start with a simple example, and then I'll explain where I will go. So let me start with a simple example of an ideal fluid. So I'll assume that we describe our fluid with two fields, the density field and vector field, which is velocity field. I will emit arrows on x, but x is a point in a 3 or 2-dimensional space. And the equations which one usually write, it's either 2 or 3-dimensional. I will later concentrate on 2-dimensional space, but now x is any dimension. And we start with two basic equations. One is the conservation of mass, conservation of number of particles, or continuity equation. And another one is Euler equation, which is basically second Newton's law written for in the frame where in laboratory frame where in Euler language where we have velocity field and density field, and this derivative is basically the acceleration of a fluid particle. Okay, so here P is a pressure. Generally, pressure is a function of density, the local function of density and temperature. But for this talk, we will assume that the motion of the fluid or gas is entropic, and we assume that our pressure is just a function of density. So these are two simple equations. In 3-dimensional space, there are 4 equations and 4 fields to specify. So this is complete system. We solve these equations with some particular initial conditions, and this gives us the dynamics of the fluid.
There's no classical viscosity.
This is just ideal fluid, no viscosity at all. Yeah, and I'll just talk about the definition of viscosity and in particular Hall viscosity. So it's convenient to introduce the momentum density, which I will assume has a relation for now with velocity field in the following way. So we'll just introduce this notation and write down equations for J instead of velocity. So what we have is the first equation is rewritten in a simple way like this. And the second equation can be written in such a way that you can see that the momentum density is conserved. So the important part here, of course, is the expression of T in terms of J and rho itself. Or I'll rather explain it, I'll rather write it in terms of rho and V. So this is the expression. So what we have is we have 4 equations here, plus constitutive relations. These are called constitutive relations, the relations which express stress tensor in terms of rho and V, and current or momentum density in terms of rho and V. So this is basically the basis of hydrodynamics. We just say that there are 2 conservation laws. One is the conservation of number of particles, the other is conservation of momentum. We write conservation laws, and then all microscopics, everything else goes into the constitutive relations of how to express stress tensor and everything else in terms of the fundamental fields, in this case, density and velocity. So this object is called stress tensor. And this is sometimes called zeroth order hydrodynamics, because there are no derivatives in the constitutive relations. So there are no, if one adds here terms which are proportional to gradients of velocities, this is what's called viscous terms of stress tensor, and this will be viscosity responsible for that. So simple comment here is that this is ideal fluid, the energy is conserved here, and it would be nice to write it in Hamiltonian formulation. So write Hamiltonian in Poisson brackets. And it turns out that this is easily possible. We just write Hamiltonian as dx rho v squared over 2 plus rho epsilon of rho. It's traditionally written in terms of epsilon of rho, which is the energy per particle in this state.
Read that. Rho, what?
This is epsilon. This is new letter, epsilon. Epsilon of rho. Epsilon rho is just a function of rho, such that if we differentiate this with respect to rho twice, we get 1 over rho derivative of the pressure with respect to density. So if I have pressure as a given function of density, I can find out what rho of epsilon of rho is, and I can write this Hamiltonian. And in addition to the Hamiltonian, of course, I need Poisson brackets to generate equations of motion. And this is a Poisson brackets.
So this step you can't do for incompressible motion.
This step,
Because you don't have an equation of state. You don't have pressures function of.
For incompressible motion, you have this.
You don't have P of rho.
You have P there, but P will not be function of rho, but will be determined from incompressibility condition.
So you can't write this. You can't do this step for incompressible.
In physics, you understand the incompressible as a limit of compressible.
Okay.
So I always can do the following. I can think that P is a function of rho, but steep function, so that it's very hard to compress this fluid. And then in the limit of the stiffness going to infinity, I will reproduce incompressible motion. Okay. Okay. And then additionally, I need commutation relation or Poisson brackets for velocities. Here notation is the following. If I put prime here, it means that v depends on x prime on different points. This is just for brevity of notations. And this is vorticity divided by density, and then delta function of x minus x prime. Okay. Is it seen what I'm writing here? So this particular term telling that different components of velocity do not Poisson commute, do not have vanishing Poisson bracket, is what is responsible for generating this term of this form. So one can easily check. This is just trivial exercise that if you take this Hamiltonian with this Poisson brackets, one generates equations, hydrodynamic equations written above. Yes, that's right. And an important point is that one can also check that this Poisson brackets satisfy Jacobi identity, which may be not really very transparent in these formulations, but if one writes it for J, then one can recognize that J's are generators of diffeomorphisms of the space, and that's why they do satisfy Jacobi identity.
I'll be a troublesome mathematician. When you do Jacobi identity, you get two delta functions. Don't you get to multiply two delta functions together?
Where? These are different points.
Different points.
This is all
Different points. So
prime means that it's point x prime. So it's
can you write a symplectic form from it?
yes. Okay. If you have general two functionals and you want Poisson commute, then this way is just a more elementary way to write it down. But of course you can take variational derivative with respect to psi, differential derivative with respect to psi j, and then psi I, psi j prime. So I can write it in terms of the Poisson bracket, in terms of this integral expression, which tells you how to calculate Poisson bracket of any functionals of density and velocity. But the idea is very simple. Then I just take variational derivative of this with respect to my fields. This is either density or velocity, and then I use this.
Symplectic form. Can you invert the tensor? Write a symplectic.
Oh, this is my especially. That's very important point. Of course, no. Of course, no.
This is not Lagrange.
Yeah, that's if I were able to write symplectic forms, then I would write Lagrangian. But it turns out that this is much trickier. That's why I stress on Hamiltonian form.
It's not degenerate, or
It is degenerate. I'm going to talk about it. I'm going to talk about it. There is a very well-known question of how to put these equations of motion in the form of variational principle. For example, as a minimization of some action, or to write Lagrangian, or any other type of formulation. It turns out that there is a difficulty, there is an obstacle, because for these particular equations of motion, the following expression okay, this is in 2 dimensions, and in 3 dimensions now it's a little bit different. It's Chern-Simons made out of velocity. Okay, so this quantity in 3 dimensions, Poisson commutes with velocity field and rho field. This is Casimir of Poisson brackets. And so, or it becomes a zero mode, and you cannot invert Poisson form and make it symplectic form. And this is, there are several names for that. One of them is helicity, and helicity of the fluid. And in 2 dimensions, it's even worse. There are infinitely many with any integer n. This all integrals are Poisson commute with any of the elementary fields, and therefore with any other, with any Hamiltonian. Omega, yeah, sorry. Omega is vorticity. So in 3 dimensions it's vector, in 2 dimensions it's pseudoscalar. There are no components, right? So in 2 dimensions this is just number. d1, v2 minus d2. So this one is omega times epsilon. Yeah, that's right. Okay. So therefore, a Hamiltonian formulation is somewhat more convenient because it produces this term through this particular term of the Poisson brackets. Nevertheless, there are particular cases in which you can write variational principle. Okay, first of all, the general comment is that even in this case, there are ways, of course, to write down variational principle. These are called Clebsch parameters. You have to expand your space in terms of velocity. Instead of velocity, one introduces parameters alpha, beta, and gamma using the following parameterization. And then in terms of alpha, beta, and gamma, one can write variational principle, and variation of which produce these equations for velocity and density. So it is possible, but it is not straightforward, and not in terms of these fundamental fields. So what I'm going to do is I'm going to now explain that.
So you're saying that?
Yeah.
Go ahead.
Well, I'm just asking a little bit. I mean, this sort of looks like del cross V would equal 0, or is it that beta has all the information about what?
Yeah. If you calculate vorticity from here, you have beta cross gamma. So beta is field also, so this is not constant. There's a 3 scalar fields. It's in 3 dimensions. Okay. So one can, of course, now extend this model, and the easy way, for example, to extend it would be to add here some term which is proportional to the gradient.
Could you say, well, let's just discuss, you said this, you make a variational principle by writing velocity this way?
Yeah.
Can you say what you mean by that?
Let me skip it because the variational principle will appear in the simpler cases, and then you will see what I mean by
variational principle.
just action. So the minimal action will produce you these equations, or Lagrangian. Write down some functional which minimizations over rho and v produces these equations. That's
Lagrangian, so the equation of motion will be the
right.
Okay.
And this is not very straightforward, but of course well known how to do that. Okay, so one way to extend this would be to write some term which is proportional to, say, gradient of density squared. And I'm also talking only about isotropic fluids. That's why I'm only looking for the scalar quantities, so there are no anisotropies in this model. So the simplest isotropic term, which is rotational invariant, will be gradient of the density squared. If you write this is sometimes called Boussinesq approximation in hydrodynamics. One can now use this Hamiltonian with the same Poisson brackets, and one obtain the corrections to the right-hand side here, and corrections to the stress tensor proportional to the gradients of density. Okay. Another way would be to introduce dissipation in the problem.
They call this stress tensor from the other side. The Hamiltonian is an integral of the components of stress tensor, so it's not the Hamiltonian for that stress.
Stress tensor is the IK here take values only 1, 2, 3. Mm-hmm. So in relativistic physics, Hamiltonian is identified with T00 component of stress energy tensor.
Oh,
this is just stress tensor.
The energy
so, yeah.
T0I, T00 is not given.
They are not given. Moreover, in non-relativistic physics, it will not be symmetric. This one is supposed to be symmetric, but the one between time and special derivatives will not be symmetric. So T0J will be associated with J, but TJ0 will be some different combinations. But this is not really important here. Okay.
You said something about another way to do something would be to introduce dissipation.
Right.
Another way to do what would be to introduce
dissipation? To extend my hydrodynamic equations.
Okay.
So this is some simple ideal one component fluid, compressible though. One can also do incompressible, and one can also consider this fluid even without vortices. That will be especially simple. But we want to make it more general, and for that, not all equations are Hamiltonian. So you have to introduce dissipation. For example, you have to. It's not possible to do it within Hamiltonian formulas. You have to add special terms coming from dissipative function, for example, and that will add the corrections to stress tensor, which are proportional to derivatives of velocity. So let me write how typically they look like.
You can accommodate dissipation in the Hamiltonian framework?
I cannot. I cannot.
But I mean,
but nevertheless, momentum conservation should still. So momentum conservation should still work. So the equation for momentum density should still be of the same form. So therefore, we have correction to the stress tensor, and let me write it with proper coefficients, which will be of this form. Or rather, let me write it what I should add to equations. So dTV plus V. So here delta is Laplacian. Okay. So in isotropic fluid, we can add the following structures in the right-hand side of the equation. And this eta is called shear viscosity. And this zeta is called bulk viscosity. So basically, whenever I have a fluid flow of this type, this is our fluid flow with shear, then there is a friction which appears between different layers of the fluid, and that's represented by this term. If I consider the motion of the fluid of, say, this type when it compresses, then additional dissipation can appear, and that's given by the term related to zeta. Okay, so these equations are not Hamiltonian anymore.
Stuff you make with the baking soda with children, put water in,
yeah,
and it has completely different viscous properties if you compress it slightly. You know,
all these non-Newtonian fluids, yeah. Okay. This happens when those terms cannot be written, when it's more complicated than this. This is Newtonian fluid. So this is.
What does this mean then? It's bulk viscosity. I don't understand it.
Oh, it just whenever you have some volume which you compress, there is a dissipation because of different parts of fluid move with different velocities, and this term just takes this dissipation into account. It's usually for gases. It's usually small. It's very small, which is okay. It turns out that you can add here one more term if you assume that parity is violated. So parity is broken, and that term will look like this. And now, I'm talking, this particular term is written in 2 dimensions. And I introduce notations that AI star equals epsilon ij aj. Or in a vector form, A star equals A cross Z hat. So
What is written there?
this is just our subscript called H, which is whole. Just notation. This whole thing is notation. It's just some additional parameter. And that parameter is called whole viscosity.
Or a function of accent.
It's in hydrodynamics, it's usually all these things, of course, are functions of everything. But in hydrodynamics, we think of this as a gradient expansion, and we assume that this is just some number. In the systems I'm going to talk about later, like quantum Hall effect, this is really number.
Your equations are some approximations when you expand and keep like this.
Right. So the logic of hydrodynamics is that we write conservation laws, we write constitutive relations, which capture the main relations, and then we add to those equations corrections which are expansions in gradient. So hydrodynamics is basically conservation laws plus gradient expansion. And this is the whole logic behind hydrodynamics. So as you can see from the presence of this epsilon ij symbol, epsilon 1, 2 is 1, and this is Levi-Civita symbol, which is antisymmetric in 2 dimensions. Its presence signifies that parity is broken by this term. So there is a special direction, which you also see from this vector form. So whenever I have 2-dimensional plane, I'm saying that there is a third axis perpendicular to that plane, and I take it up. And then for every vector A, I can introduce A times Z hat, which will be in this particular case in this direction. And this is precisely this velocity enters this term. Okay. The nice part about this is that
this comes from the correction to TIK in derivatives of V, right?
Yeah, this is what my next statement is the following: that these guys cannot be included into Hamiltonian, but give corrections to TIK in derivatives of velocity. This guy also gives corrections to TIK in derivatives of velocity, but it is non-dissipative, and therefore we hope and we're sure that it can be included in the Hamiltonian formulation. So the meaning of this is the following. Remember, the first term is the dissipation due to shear. That's one way to say it. And more canonical way is to say that whenever you have shear, you have forces, friction forces, which appear in this direction. So whenever you have 2 layers going by another, then there is a friction force which opposes to that. Similarly here, whenever I try to compress, there is a friction force which opposes this compression. And this friction force is parallel to the displacement, so these terms do perform the work on the fluid, or dissipative work. And in this particular case, the physical meaning of this is that whenever I have shear, there is additional pressure which appears perpendicular to that shear. This is kind of a little bit counterintuitive. So you have a fluid, you try to rotate it, and instead it tries to compress. And this is the meaning. So this coefficient is basically a coefficient of proportionality between the shear and pressure in the orthogonal direction. But because pressure is always orthogonal to the displacement, this is a dissipation-less term, and therefore we can include it in Hamiltonian.
Could you say this term again, the picture of what it means?
This picture?
Oh yeah, this third term, the Hall viscosity.
Yeah. So whenever you have gradient of velocity, which is the following, so suppose it's a smaller velocity, bigger, and so on and so forth. Usually it's done by putting 2 plates experimentally and then or moving one plate relative to each other, and then measure the resistance force. So whenever we create shear like this, in addition to this resistive force, which will be in this direction, there will be also force in perpendicular direction. And the coefficient of proportionality between gradient of velocity and the force in this direction is called Hall viscosity. So this is one more component of the stress tensor for isotropic fluid in 2 dimensions, which is does not respect parity. So if your system respects parity, you just forget about this term, and it almost never appears in any literature.
A gradient of velocity due to like a vortex or something. Right?
It is related, so it is related to vorticity in some interesting way. So I would like to claim also that if you have something like superfluid with finite density of vortices, then macroscopically it behaves as fluid with Hall viscosity. These statements like that. But yeah, so basically, roughly, you're trying to rotate your liquid, and instead it's compression forces appear. Okay, so now the first thing would be just to include, so forget about this term because they're not Hamiltonian, and include this term in the Hamiltonian formulation, which turns out to be a very simple exercise. And my next part are yeah.
I mean, the whole idea, you said there are forces perpendicular to the gradient.
Right.
So in this system, it all seems to come for free because it's Hamiltonian. The forces are perpendicular, but it's somehow somebody has to pay the price, right? I mean, there must be whatever it is that's holding the thing in 2 dimensions.
There must be some system where parity is broken, and for this, either there should be some helicity. For example, the molecules should be like spirals, which are aligned in some direction, or you can have external magnetic field. So the terms of this type were known in magnetohydrodynamics for a long time. So in a plasma and magnetic field, they were not even put as something special or additional. They just were part of the viscosity tensor. The term is actually the following: the viscosity tensor is actually 4-rank tensor which connects strain and stress. In physics, that's general. And in isotropic 2-dimensional fluid, it's possible only to have 3 non-zero coefficients in that tensor, and this Hall viscosity is one of them. In isotropic and parity invariant fluid, it's possible to have only 2. And those enter any textbook, but this one is usually missed. Okay. So again, the first step will be just very, very quickly, I will show how to incorporate this term into hydrodynamics, and then in Hamiltonian way, and then I will explain, we'll give some example of the model, which I claim reproduces a lot of features of fractional quantum Hall effect, and it's very classical. So it's classical model. There is nothing quantum there, which is quite weird. Okay. Historical note is that these are Poisson brackets, or rather at that point they were quantum commutation relations. It's very interesting that these relations appeared first in quantum physics. They were written by Landau in 1941 when he talked about superfluid helium and hydrodynamics of superfluid. And he derived those, we just postulate here those expressions to reproduce equations. Landau actually derives those from microscopic physics. The way he did it is actually, let me just write down this as an exercise, which is very easy to perform. If we introduce the following object, so the sum here, let me put alpha. The sum here is over particles. So my particles are characterized by their positions, and this is the density of particles. Each particle contributes delta function to the density. Then I can also write the current, which I will define in the following way. P alpha I. Let me actually write it in vector form. It will be a little bit easier to understand. Okay. So this is the density of particles. This is the density of momentum. At position of every particle, I take the momentum of the particle and multiply it by delta function. So if I integrate J over some volume, I will get sum of P's, which is the total momentum of the system. And then, of course, I have P alpha I x beta j, the canonical Poisson bracket between momentum and coordinate of the particle is to be delta alpha beta, delta alpha j. So only they're non-zero only for the same particle and only when components are the same. That's standard. So if you just take this as an input and perform the calculation of Poisson bracket, say between rho and j, then defining also j to be rho times v, one obtains all these Poisson brackets. Here there is a dangerous division by sum of delta functions, but you have to do it only at the point where a particle is. And in principle, you can do it without velocities, talking only about momentum density. And this is a little bit safer, because for momentum density, you should not divide by density. But this is really a tricky point. Also, in quantum physics, you have to symmetrize this. So it's like p times delta plus delta times p, and so on and so forth. All expressions should be symmetrized. But it worked in quantum physics. And then, of course, you can do the same using Poisson brackets in terms of commutators and derive the same relations. OK. So let me make another digression. Let me write down some variational principle. So let me write down one more example. Sorry. Let me first do what I promised to do and just write down the Hamiltonian and Poisson brackets, which produces whole viscosity. Okay. Let me write down the following Hamiltonian. Another form would be if I open parentheses and do integration by part. Here the terms are of the quadratic ingredients of density, so they're not important. So let me assume that the Hamiltonian has this form, where rho and v again satisfy the previous Poisson brackets. And so basically we add one additional term, which tells me that whenever I have vorticity, and again, OK, from now on it's two-dimensional. So therefore so this is not vector, but number in 2 dimensions. So if I have this Hamiltonian, and one more addition is that let me assume that current is not related to velocity by just simple formula rho v, but has additional correction psi gradient star of rho. Okay. Then using this Hamiltonian and the previous Poisson brackets for density and velocity, we can easily derive the following equations. Where Tik can be written as rho vi vk plus, actually let me write it in big letters.
Excuse me, do you need the dot term to derive these equations?
This dot term is just the square of this, and I will not need it later.
No. I'm asking, do you need the term in order to derive this equation of motion? So suppose I drop these terms and start doing whatever you suggest.
Just start from here. Yeah, you can do that. Yeah, you can do that. The exact form of the stress tensor with all derivatives will depend on these terms and whatever terms were present there in the beginning. So this term is not that it's not observable. It will be contribution to the stress tensor.
So if you keep those terms, there would be additional terms in the equation.
Yeah, generally I have to do the following. I have to start with this plus a of rho gradient rho squared, just the next correction in gradient of density. Then this term will just correct this term. It will correct this a. And I can write expressions with all these a's, but the reason I'm doing this is I want to identify the whole viscosity, which is the first derivative in velocity term. So for this exercise, these terms are not important. And they're not important in what I'm going to say now, but maybe important for the second part.
Why is there this second term in the current?
I'll explain that. So far, I just postulated, because remember that the logic was the following, that I have conservation of momentum and conservation of number of particles. This is conservation laws. And then I need constitutive relations, which tells me how my current momentum density is expressed in terms of density and velocity. And usually this is what people say, that if there are particles and they move with velocity v, they also carry momentum, and this is what happens. What I will try to explain is that there are sometimes these additional terms appear. At this moment I just postulate, but I will explain the physical meaning of this, where it comes from. It's basically from particles rotating in circles. So this term will appear, which will shift. So basically the current density, the particle current is different from momentum density. This is in principle possible because we are talking about some effective hydrodynamics of a non-microscopic origin. And this term is the most essential part of the story. So let me do the following. Let me now write down what this new TIK is.
Momentum current.
This is momentum current, momentum density.
Centrifugal something or other.
So if you think about free particles, just particles, then of course the momentum is just rho times v.
Right, but now it's
But now if you think of particles rotating or coarse graining your description and talking about microscopic variables, then this relation between velocity, which is necessary to describe the flow, and momentum density can be shifted. Okay. So again, if we do just straightforward calculation, we obtain the following expression for stress tensor. I'll explain what tilde is in a second. And this is two-dimensional again. Okay, the dot terms are terms which are proportional to gradient of the density squared, and they are not important for the following. And this part is precisely what should be identified with Hall viscosity. This is how Hall viscosity enters into the stress tensor proportional to the gradients of velocity. And one more thing is that, of course, that V tilde is defined here as V plus psi gradient star log rho. So basically, if I rewrite everything in terms of J, this will be some coefficient in front of the derivatives of J, and this is Hall viscosity. Okay. So basically, that's it. So we have Hamiltonian. That's the first result which I wanted to show. Very simple one. That if I have this Hamiltonian and this constitutive relation, then as a result of applying the same Poisson brackets as before, I can obtain this equations of motion with the following stress tensor and with Hall viscosity. There is some unusual term here, which, for example, is totally avoided in Landau-Lifshitz. Not that it's completely prohibited, but it's very unnatural to have, for example, in elasticity theory. Because what it tells you is that there is a correction to pressure due to the vorticity of the fluid. So whenever you have fluid rotating, the pressure is corrected. intrinsic pressure is corrected. The pressure usually comes from the interaction between particles, which is a function of interparticle distances. And of course, if you rotate system as a whole, the interparticle distances do not change. Therefore, in Landau-Lifshitz, the terms in stress tensor which are proportional to gradient sense velocity are always looked for in the symmetric form. Only in this combination. So asymmetric combinations is omitted because asymmetric part, which is the vorticity, does not change interparticle distances. So this term is unusual for normal fluid. Of course, now all rules are off because we are talking about some effective one component hydrodynamics of some fluid which is in principle quantum and interacting. But nevertheless, it's also nice to notice that if alpha equals psi, which is still non-trivial deformation of original theory, if alpha equals psi, then this term is not present, but this still is present. And you can see that this psi actually comes only from the relation from the constitutive relation. So this psi is more important than alpha, because that psi determines the whole viscosity. But if you want to get rid of the term which is unwanted, then you put alpha equals psi, and then it's all consistent. And what I wanted to stress here is that notice that if I introduce this v tilde from the very beginning for the particular case of alpha equals psi, then my Hamiltonian is just dx rho v tilde squared over 2 plus rho epsilon of rho plus so on and so forth. So what I could say, and this is basically probably the most compact way of telling the results, that if I just take this Hamiltonian, which is the same Hamiltonian as I usually take for ideal fluid, but I deform Poisson brackets such that v tilde and v tilde Poisson commute in the following way, where you use this formula to actually calculate. I don't write it; it's pretty ugly, but it's much better in terms of currents, and I'm pretty sure it has geometrical meaning, which is not easy to discover. But
if your fluid is composed of particles with spin, then alpha in principle should not be equal to psi, right? I mean, because there could be correction to pressure from the interaction.
That's true. The model which I will show very soon has different alpha and psi. So it's not necessary. But I'm just saying that if you just take original Hamiltonian with Poisson brackets, which involve this redefinition of v tilde, which are very easy to calculate. I just take this v tilde, find Poisson brackets with itself, and then I replace v in the right hand side by v tilde again. I have closed Poisson brackets for v tilde and rho, which satisfy Jacobi identity, obviously, because this is just redefinition. And then I take the initial Hamiltonian, but I say that by some reason v tilde has different Poisson brackets. Then this will be fluid with whole viscosity and without this extra pressure term. Okay. So the origin of whole viscosity of the term, by the way, the term whole viscosity was invented by Nick Reed in 2009. Before that, people called it either didn't call it anywhere, just some part of the parity non-invariant part of stress tensor, or odd viscosity, or Lorentz shear modulus. There was a name, and Nick Reed said that there is a conductivity which is dissipative, and there is a whole conductivity which is dissipationless, and there is a viscosity and there is a whole viscosity. So, the term whole viscosity is kind of getting more and more popular. Okay, so. So let me say a few words to demystify this weird relation between momentum density and velocity. Show you some very simple arguments showing how this can appear. And this is related to what Dima just said, that suppose that I have a gas with particles which have intrinsic angular momentum mu, which is oriented perpendicular to the plane. So each particle is not elementary, but has intrinsic angular momentum. You can think of this as orbital angular momentum, for example, small circles. So all particles rotate in small circles due to the presence, say, of external magnetic field. Then let's calculate the angular momentum of some some small piece S of a fluid. Let's integrate over S of dx. And the angular momentum is of course, the angular momentum of the fluid moving as a whole. This is R cross P. But in this particular case, plus mu multiplied by rho. Because every particle has additional angular momentum mu, so I have to add this. And integrating by parts, well, I should do this. Integrating by parts and dropping the surface term, we obtain R cross rho V plus. Well, let me throw here in parentheses. Okay. If you integrate by part and you get divergence of R, which is 2, then 2 cancels this 2, and you have mu times rho, which is original rho. So what you see is that to describe angular momentum of this, the total angular momentum of this fluid, including this elementary angular momentum of a fluid particle, then you have to shift the relation between velocity of the flow and momentum density in the following way. So we call this J. So you should identify Hall viscosity eta H, which is psi times rho, as mu over 2 times rho. And that's a formula which Nick Reed first suggested for quantum Hall effect, which tells that the Hall viscosity is basically the half of the angular momentum of a particle. So this is a simple argument. He did it in more general settings and for quantum system too. But this is the origin of that interesting relation between momentum density and current. Okay. Finally, let me give you example of some theory which has Hall viscosity, which is of a charged fluid in external field, and which reproduces many features of the quantum Hall fluid. And now we'll have all these formulas, so it will be very easy to write it down. So let me write down also the external potential term, so just potential of external field. And in principle, one can write also corrections to the equation of state. But I will pay attention mostly to this term. And let me assume that velocity is it's actually the shorthand way to write down the following relation. So what I'm saying is the following, that velocity is just a notation here. Don't forget that it's vector field, independent vector field. So velocity is just a notation for this combination of symbols, where pi is and rho are actually two independent fields with Poisson bracket of this type. So this is canonical Poisson bracket of field pi and field rho. And here also there is a new quantity phi, which is beta integral log x minus x prime rho of x prime. So phi actually is just a solution of Laplace equation. Beta is parameter. This, unfortunately, yeah, that's always a problem using pi as a notation. So this is 3.14 and so on and so forth. And that one is a field. So yeah, sorry. Okay. Actually, if you take this as a definition of V and take the Poisson bracket of V with rho, then of course you obtain the previous. I'm pretty sure that I erased it. Let's see. I'm lucky. No. Okay. So if you take Poisson bracket of V with rho, then of course this is a gradient of a Poisson bracket of pi with rho, which is the gradient of delta function. And this is our old relation. But if you take Vi and Vj, where Vi and Vj are defined in this way, then you obtain somewhat different result. You obtain minus 2 pi beta, I think, delta of x minus x prime, which is very well consistent with the fact that this is the vorticity divided by density. And if you take vorticity of this field is 0, and vorticity of this field is a Laplacian of phi, which is 2 pi beta times rho. And you divide by rho. Okay. In fact, there is also this A. And if I have external magnetic field, then instead of this, I will have minus 2 pi beta rho minus rho 0 divided by rho.
Yeah, well, what is A on this one? A was capital A.
Capital A is external vector potential such that cross A is B, constant magnetic field. So I have two-dimensional plane in a perpendicular magnetic field which is constant. I introduce some vector potential and some gauge which correspond to that magnetic field. I just define my combinations of fields this way. I call it V. I take this Hamiltonian with this V, and with this relation should be
What about ij indices?
epsilon ij, yeah, 2 pi beta rho minus b. Yeah, that's a good question. Otherwise, it's symmetric. So yeah, well, otherwise it doesn't make sense. So epsilon ij, and this is the density minus some background density, which is defined by the constant magnetic field. So this relation is quite interesting. It basically tells you that, well, there is also a relation that V is not independent field anymore, but has the following properties, that if I take curl of V, then curl of the first term is 0, and curl of this term is density. It's equal to minus 2 pi beta rho minus rho 0, where rho 0 is just magnetic field divided by 2 pi beta. So this fluid, whatever it is, has a very unusual relation that whenever we try to add particles there, vorticity is created, or any vortex carries particle number. And this beta defines of how much the vortex, what's the relation between vorticity and particle numbers. So that's the first thing that you observe from here. And second, because of that shift, we already know that if I calculate Hall viscosity, then I obtain Hall viscosity alpha from that calculation. This also can be corrected slightly by adding here a very natural term, which is psi minus alpha rho times b, which is also possible to have in the presence of the orbital momentum for particles. The particles have also magnetic momentum, which interacts with external magnetic field. In that particular case, if I calculate electromagnetic current varying over A, then I obtain the relation that current actually equals rho v plus psi star rho. So what I'm trying to say is that this is some hydrodynamics with postulated Poisson brackets, and you can just take this hydrodynamics and study its properties, and you obtain the following properties. First, there is a vorticity-density relation. Second, the Hall viscosity turns out to be equals to psi times rho. Secondly, you also can calculate different other observables from quantum Hall effect physics. For example, you can calculate.
Where did the beta come from?
Beta so far is just parameter. I have 3 parameters in the alpha, psi, and beta. Beta emerges here. So basically, in the definition of velocity, there is a beta which is hidden in phi, and phi is related is a density. So basically, it appears from here. So the way to write it down in this form involves this beta.
Things are spinning.
Yeah, that's right. That's right. So I have three parameters, alpha, psi, and beta, and I can take this fluid and calculate different properties of this fluid, and then try to match it what was calculated for fractional quantum Hall effect with particular Laughlin's wave function as a test functions. And it turns out that I can do it, and that defines all of those parameters. For example, this psi turns out to be equals beta over 4.
What was the it in that last sentence? You can do it? What's the it?
Okay, you can take this theory and calculate different properties of this theory. For example, Hall viscosity. And you calculate and you find this. This is phenomenological because I didn't explain where these parameters come. Then you can take fractional quantum Hall effect theory, which is totally quantum theory with Laughlin wave function as the ground state. And you can try to deform it and calculate Hall viscosity, and it's known how to do that. And they find it that it is equal, so if you introduce the filling factor, which is important for fractional quantum Hall effect as 1 over 2 pi beta, then Hall viscosity is equal to by beta over 4. Also, in fractional quantum Hall effect, it is known that vorticity is related to density exactly by this relation, with this beta to be identified with filling factor of Hall effect. Sorry, without 2 pi. Beta, for most interesting case, beta is just 3. This is the most elementary Laughlin state for Hall effect. Okay, then you can calculate the static structure factor, which is the density-density correlation function. This is hydrodynamics. I can linearize it and calculate density-density correlation function. So this is effective Hamiltonian for which mimics quantum Hall effect. It's classical, so there are some problems with this Hamiltonian which do not. It should be classical, except for that the parameter which is written in dimensional forms is alpha proportional to h bar. But yes, this is effective classical Hamiltonian. There are still some problems. I don't want to claim that this is the theory of fractional quantum Hall effect because of a very important reason. There is a problem with mass. Here I cheated in a big way by dropping mass of a particle everywhere. But there are two masses which are important when you talk about fractional Hall effect. One is the mass of electron, which is basic, which is underlying particle for the whole thing, and another is effective mass, which is determined by the gap separating of fractional Hall ground state and the excited states. So in different quantities, these masses come in different ways. In all collective properties should not even know about the bare mass of electrons. They should all written in terms of that effective mass. Here there is a problem because when you look at the excitations, you have the gap in those excitations, which is given by this mass, but should be given by bare mass because of some rules. So there is still some problem which are not solved by this theory. But I'm saying that a lot of phenomenology of Hall effect come from this theory correctly. So the static structure factor is basically density correlation function is given by 1/2 k squared, 1 plus alpha k squared. And it was also calculated, so you can get alpha from there. And alpha turns out to be beta minus 2 over 4. And then you can calculate Hall conductivity there, or even wave vector dependent Hall conductivity. And it turns out that the Hall conductivity is given by the following formula for that fluid. Plus, of course, higher order in K. So you can see that it's already some prediction that the wave vector dependent term in the Hall conductivity is given by this particular combination of the quantities which we determined. And this is, okay, you can beta minus 4 over 4. And indeed, this was calculated. This can be easily calculated. For beta equals 1, these are like free electrons in magnetic field. So that's all these formulas can be checked directly by simply non-interacting calculation. But this coefficient was also predicted by Son and Hoyas, and it follows from some important, from Galilean invariance, basically from the symmetry, which is present in this effective Hamiltonian. Okay. And finally, the last comment, okay, can I take a couple of minutes just to finish? The last comment is that looks very unnatural here, having coefficient here, which is beta minus 2 over 4. But there is a simple, well, rather relatively simple explanation of that particular coefficient, which comes directly from Laughlin's wave function of Hall effect. And this is somewhat mysterious because it looks like there is a one-to-one relation between this classical Hamiltonian and potential quantum Hamiltonian. So let me do the following. So let me remind you what Laughlin wave function is, characterized by parameter beta. So beta equals 3 for the most important example. So this is the Laughlin's wave function. And let me write psi beta squared, absolute value, and try to write it in terms of the density of the fluid. I want to have quantum hydrodynamics, so I want to have my wave function as a functional of density. So I want to rewrite this simple looking function in terms of the density. And well, the way to write it is the following. It's e to the 2 beta okay. Well, this is very naive way of writing it. What I did is I just exponentiated this. I get sum over I smaller than j of log zi minus zj. Okay, and instead of this, I substituted it by two density fields, which is sum of delta functions, and then naively this reproduces this term. Okay, of course there is this term, which is written as rho of x squared over 4 over 2 because it's all squared. Integral dx. This is just external field term, but there are two subtleties here. One subtlety is that here I is not equal to j. They cannot coincide. Here, when I write it in terms of sum of delta functions, there are terms which are diagonal terms in this product where I equals to j. So basically, I'm taking into account here more than I should. So I should subtract that. And what we say is the following, that the particle actually goes over orbit, which is kind of smeared. So the minimal distance between particles is not arbitrary, but 1 over rho itself. And using this type of speculations, you obtain that the additional term should be added here, dx rho of x log rho of x. Okay, I'll not spell out this, and I'm not sure that coefficient is correct. It's probably beta over 2 here. But so basically, this is comes from ultraviolet regularization of this term. So then particle coincide, you have to take special care of it. It's very easy to get from estimate, but important thing that there is nothing else essential comes in. Okay, and then this is not the whole story, because also there is, if I calculate, for example, the integral over absolute value of psi squared over particle coordinates, this is norm of the wave function, it should be now equal to the functional integral of all densities of psi squared, where this psi is the functional of density. And there is entropy term here, Jacobian. When you go from integrations over particles coordinates to the functions, you can actually move particles a little bit without changing the macroscopic density of the particles. So you can estimate that here you have, when you go to d rho, you have here volume, which is 1 over rho, multiplied by the number of particles. So multiplied by rho of xi multiplied by the number of particles. And when you exponentiate, you get the same term, but with these entropy corrections, which give you beta minus 2 here. So now, if you now say that suppose that I trust this wave function as a wave function as a function of density, which field, what will be the operator which annihilates this wave function, which is similar to velocity? And you can easily see that if I take delta over delta rho, R here is this is just the curl of A. You can get this, and from this term, you obtain indeed logarithm of density multiplied by beta minus 2 over 4. So this should be identified as the quantum version of my pi field, which is a canonical conjugated field to rho. This is phi.
I don't understand. I thought operators act on wave functions, not absolute value squared.
That's true. When you formulate hydrodynamics, you formulate it in terms of bosonic functions. So you need some condensate and functional density, which is bosonic. The original wave function had this term zi minus vj cube, and this cube made it antisymmetric. So what you should do first is you should do the singular gauge transformations to remove the phase, or basically to look for the wave function which depends on the absolute value. This is a tricky point because I cannot really argue well that there is no transverse term in addition to this coming here, which depends on arguments. But basically, what I'm doing is that I'm first removing the phase, and then I'm trying to write down an operator which annihilates the function without phase.
Should I try to understand it in this way? You are sort of introducing another variables, this rho.
Yes.
And try now as some sort of collective variable.
Right.
And now try to quantize this theory in terms of these collective variables.
True. If we trust this classical series, then the question is just to quantize this theory. So then it's maybe complicated, but it's clear what the problem is. Here, what I'm trying to do is I'm trying to build a bridge to microscopic physics, and this exercise was done precisely in Calogero model. You actually can see the remarkable similarity of all these formulas to Calogero model. To hydrodynamics of Calogero model. But anyway, so what I'm trying to do here is I'm trying to start with the particles which are described by their positions and velocities, then introduce collective fields of the type of Landau, like the density is sum over delta x minus xij, and then try to write collective theories from microscopic. And I'm trying to say that I'm coming to something like that. And unfortunately, the way we are doing here now is a quantum. There, I understand really well on the classical part, although quantum counterpart can be written the same way. But
I need your last remark this way, that the absolute value of psi squared here is going to be something like a wave function, ground state wave function.
Right.
This collective.
Correct. Yes. Correct.
It doesn't look like a derivation to me.
Oh no, it is not derivation. No, I'm just saying that, yeah, okay. It's far from derivation. I'm saying that this coefficient can be understood as coming from that exercise. But I mean, what I'm actually doing here, and I'm saying that if instead of pi you get delta over delta rho, and try to find the function which is annihilated by this operator with this shift, then you obtain absolute value of that function written in terms of rho. But this is not really derivation. Unfortunately, we tried to do it, and many of these things were done with Paul Wigman, I should say. So we tried to derive it from truly microscopic picture step by step, like it's done in Calogero, but something is missing there. There are no nice identities which we have in 1D, which allows us to do this way. So let me stop here. So what I showed is that Hall viscosity is very simple to include in just simple hydrodynamics, and there is a theory here, which is defined by the Hamiltonian, which looks like quantum Hamiltonian, which could annihilate Laughlin state written in terms of density. So that's it.
Any more questions?
I have this.
Yeah.
I'm not qualified to ask this question, but so if you take this description, and you said there are a couple of problems with the bare mass and all
Right.
that stuff. Right. Suppose you just tried quantizing this, and then the renormalization theory might produce the desired effect.
I really hope for that, because the one example which is encouraging is the following: that this psi minus alpha, if you take the values which we derived, is actually 1/2. So the difference is very simple. It doesn't involve this parameter beta. It's just 1/2. So this is nothing else but the way to write 1/2 h bar omega c times rho. 1/2 h bar omega c is the ground state energy of a free electron in constant magnetic field. So this is just zero energy. which should be, from the point of view effective theory, it should be thought about that you start with some quantum theory, and in one loop approximations, the first quantum corrections give you zero energy, and this zero energy just enters classical expression as it is. So I do hope that if you start with this, with whatever parameters are here, and try to quantize it, then it will be resolved. Of course, there are also issues that this is the minimal stuff, and of course you can add a lot of additional stuff which are proportional to gradient squared, and so on and so forth. And the question is how universal all these properties which we are talking about. And it seems that whole viscosity is relatively universal in translational invariant systems. But for example, this static structure factor might be not, because adding just gradient of density squared, you might change it. So another way of doing this is to try to find some minimal model which may be even integrable, because and there is a hope, because quantum Hall effect projected to the first Landau level is more like one-dimensional theories than two-dimensional. So maybe there is some analog of this which is really solvable, and solution looks like solution of Calogero model, but we don't know that. I'm not sure that I answered.